inviting me. So I'd like to give a rather elementary introduction to flow homology. So my apologies to who know more actually. Anyway, so the time for first lecture is so what is Lagrangian homology? And infinite algebras and its formations. Second lecture would be examples of symplectic Toric manifolds. Okay, so let's start with symplectic manifold. So we have closed two form, which is non-degenerate, and so just let me briefly review what is Hamiltonian vector field. If you have a function on M, then so this symplectic, you can use symplectic form to somehow transform. So vector fields and one forms, because this is non-degenerate, and the precise formula is just given by this way. So just if you plug in vectors, this should hold true. And so this vector field is called Hamiltonian vector field, and if you're not familiar, then the main example you might just consider is this height function h, and then symplectic form here, the standard symplectic form, you can also think of it as d theta with dh, except at 2 points. So away from these 2 points, you can think of it this way, and it's not hard to see that you have to kill d theta to get dh. So what you get, so xh in this case is just the rotation, d theta. So I'll also write phi h of t. This is flow of this Hamiltonian vector field, and flow is just rotation. Okay, so when one say flow homology, there are many versions of flow homology, but in symplectic context, we have the main two versions. So one is this periodic Hamiltonian flow homology, or homology, and this is given by generators. So the chain complex for this homology series, the generators are given by closed orbits of xh. So for some non-degenerate Hamiltonian function h, you consider closed orbits of xh. So it's time 1. So you have a vector field, and after time 1, you want to come back to the original point. So such an orbit are generators. So if you have such an orbit, so you set up your chain complex to be direct sum over maybe G2 of generated by these closed orbits.
Is H a given function, or
so actually one proves that flow homology actually doesn't depend on H. So you can generate any generic function H. But not actually generic, but then it has to be non-degenerate in some sense. And differential of this chain complex is given by, so if you have a 2 orbit, let's say gamma 1 and gamma 2, then you count some holomorphic maps, connecting these two. So what I mean by this is something like boundary of this gamma 1 is given by the sum over all gamma 2 and count this. So this is the count of somehow what's called pseudo holomorphic cylinders. So so what we do is we consider infinite cylinder, so it's R times S1, and you consider maps U such that this map satisfies, if you write this as coordinate S and T, then U satisfies the following formula: partial U partial S plus J partial U partial T equal to 0, or actually certain some perturbed equation. And, okay. So why, right? I mean, so why one should define a differential by counting these kind of holomorphic maps? And so maybe I'll explain in another version. So the version I want to talk about is this Lagrangian homology. So in this case, we have suppose we have a pair of Lagrangian submanifolds L0, L1. Lagrangian submanifolds. So Lagrangian submanifolds are just excuse me, is there a degree here? Degree, yes, there is a degree. So you can define a certain kind of index called Kondi-Gender index. So roughly speaking, you just choose some. So it's not well defined, but somehow you choose. Suppose you have also an additional choice of a disk, bounding disk, then somehow you trivialize and see how this Hamiltonian vector field twists your symplectic manifold around.
Asking the boundary, does it shift some sort of degree?
Yes. So that's what I mean. So actually you think of it as a map from this disk to this disk, and then the dimension of this pseudo-homomorphic maps are given by the difference of the index. So if the index difference is 1, then you have a one-dimensional moduli space, and because you also have always time translation, so if you mod out by time translation, then this you can actually count because the dimension is 0. So that pseudo-homomorphic cylinder should be isolated. So it's isolated. So there one can define a suitable notion of index such that the difference of index becomes the dimension, and so that's the degree. So it always increase or decrease by 1 by your condition.
Generated sign can be
It's finite. No, I mean you can have many.
In this example, every
Look at really.
there are uncountable many. In this
I think
example,
it's time one orbit, so
Within one.
it has to come back at time one.
yeah.
So I think you only have finite many.
In this example, in the sphere case,
Mhm.
what is closer?
I mean,
What is
it has to be time one, so I mean, what depends on your scale. Maybe there is only two. But I think this. I'm not sure if this is non-degenerate. Right. So Lagrangian manifolds. So the manifolds where symplectic form vanishes. So the main example is like something like Rn in Cn, where symplectic forms are dxi, where it's dyi, the sum of. This is the standard symplectic form. Then if you have Rn, then the vectors here are always only of the form ddxi. So if any two tangent vectors come from Rn will be 0 if you put in this symplectic form. And if you move it by some element of un, then it's still Lagrangian. So each tangent space looks like un times Rn. So that's somehow Lagrangian manifolds. And dimension of is then in this case we look at two Lagrangian manifolds, and so given two Lagrangian manifolds, you want to define a flow and certain chain complex. In this case, generators are given by intersection points, L0 intersection.
Are you assuming that the manifold is a closed manifold?
So M, let's say M is compact. Sometimes you actually allow a certain kind of infinity of M. So that's something like geometrically bounded, like in yesterday's talk. You need some assumptions. Otherwise, some assumptions so that this form curve does not escape to the infinity. So that's geometrically bounded means by some maximum principle of complex geometry.
They do floer homology, some kind of boundedness, like compactness is needed here, so that this generators are finite.
Yes. Yeah, indeed. If you in the non-compact setting, you have infinitely many generators.
Because you have a cylinder
yes.
rotating.
Yes.
All orbits are.
The case of cotangent bundle, you get somehow homology of loop space. Okay, so let's say everything is compact. And so we look at generators, let's say something like P and Q, and now in this case differential. So differential is given by counting pseudo-holomorphic strips. So in this case, you consider R times interval, and you make a condition that the upper boundary goes to L1, and lower boundary goes to L0. So this goes to just L0.
I mean, what is the dimension of L1 and L2? N-dimensional. Right?
No, this is always half-dimensional.
Right.
So they're generically they intersect at finite points.
Oh, so this R1 does not necessarily work. Okay, so only those three.
Yes, so this, so these are maps.
Mm-hmm.
So inside the map.
What do you mean by generators?
So again, you set up like P is in L0. And then the differential.
This is different setting of the homology.
Yes. So the generators here are closed orbits. Here intersection orbits. But this is actually this is includes the other one. So if you consider like M cross M and diagonal lagrangian, somewhere this is more general. And okay, so now we define something like P is sum over Q of NPQ of Q. Okay, and NPQ is this general equation with these boundary conditions, and you count isolated strips. Yes.
This is closed string and open string.
Yeah, this is closed string, and physicists call this is open string because. Yes.
What's the time direction and the current direction? Here, this T is time direction. The gamma 1 is time direction.
In physics, yeah, this.
Original thing. So T is the gamma 1.
Yeah, I mean, so you define product something like.
Time is the.
So this is some kind of composition. So I think the time you mean this direction.
S is time direction.
S is
T is not. T is a parameter, right? Here T is already time direction, right?
T is time in as a Hamiltonian flow, but I think but the time you mean, I think is this direction. Yeah, as the string moves.
But how there?
Here, not the string, but actually the path moves. So this path moves. So and you can think of actually so these actually arise as some kind of Morse theory on path space. So these are like gradient flows.
This vertical line is what here?
So this vertical line?
Yeah.
Which one?
Which direction?
This one?
This direction.
So actually you can just think of some kind of path space from L0 to L1, and then you can define a functional A, which is some kind of area functional. Functional, then the gradient flow of A is this geomorphic curves. So I'll just write pseudo this almost complex structure as just J, and so I mean one can just do it in a precise way, but I think more just maybe not correct, but intuitively, what you can think of is, suppose this map is U, suppose you have U, then, so this direction is partial U, partial T, and if you apply complex structure, So you won't find a flow which flows this way, but if you apply a complex structure, you get some direction like this. So this is J partial U partial T. But your flow is actually opposite of this direction. So partial U partial S minus partial U partial J or partial T. So this is simply partial U partial S plus J O.
Which is S direction and which is T direction?
So this is S, this is T. Anyway, so this may not be, I mean, there is a correct formulation, but it takes some time. Like, anyway, so the functional is really looking at the area, and if you see the critical points of this area functional is when you are looking at the change of areas, and when it meets, then this is the critical point of area functional. So
that's one dimension of the length, or
which one?
I mean, this you are mapping the image of R plus I to
yes,
U, right?
Two-dimensional, yes.
So this is
so
two-dimensional, and then you say area function. So it's just the length of it?
So if you want to do it precisely, then you have to actually choose your reference path. So this is reference, and any path you can actually look
this
at
area.
the area. Simply the area of this guy, and then these are the critical points. Okay.
Another silly question.
Yes.
This R plus I is non-compact.
Non-compact. Yes. Yes.
So what you mean by U mapping from there to this
and so you
so
want
the ends go to all points?
yeah, the end converges to P,
I see.
and this end converges to some intersection point. Yes. Degree. So that's okay. So once you fix your reference path, then you can talk about degrees. Look at this, how the tangent space behaves. So then you can pick a trivialization, and because this tangent space locally looks like un times Rn, and you can look at how many rotations in un. Like if you take determinant, then you can catch the rotations. Somehow, I mean, these are like not connected, but somehow there is a way to connect them. If you fix a way to connect them, then you can actually somehow catch the loops. So it's really look at how the tangent space change, and that's an index, and so that's called Maslov index. Anyway, so index is given by Maslov, some kind of Maslov index. And so at the end of the day, what's expected is that because its generators are given by the intersection points, so if we have some certain flow, non-trivial flow homology, maybe the rank of this, then we know that the actual intersection number should be bigger than rank of this flow homology, because there should be as many generators. I mean, the generators are intersection points. So if flow homology is defined, and also an important property is that if flow homology is defined, one can prove that the floor homology is isomorphic even if one changes either of the argument by a Hamiltonian floor. So you can change L1 by Hamiltonian floor, or you can change L2 by another Hamiltonian floor, and it's still isomorphic.
Floer homology defined or?
Oh, so I explained why you need this. So in the Lagrangian case, actually, this to remove this dot takes about 1,000 pages. Anyway,
before you you have changed. This is a graded, and you have grading, right? CF.
you don't actually you have
You
to
don't care about this. How do you define homology here? CF boundary,
you can
and taking second times, then this one goes to 0.
yes. So you want to prove that some of this. And there is certain notion of index. Once you fix the reference path, then you can define index rigorously.
But you just consider the CF the whole, and then
Yeah, you can also do that.
maps
Yeah,
to
you can also do
and
that.
then floer homology is defined without degree.
Yeah. And also, one might expect that this also makes sense, although they don't intersect transversely. So what is the intersection, right? But from the above, it should be, if this exists, it should be isomorphic to floor homology of pH of L and pH of L. So you can actually shift one of the Lagrangian by Hamiltonian isotopy, and when you have a Lagrangian, you can always shift yourself, the Lagrangian itself, to another one which is transversal to itself. So this is well defined because if L intersection pH of L is transversal. So this actually, one can talk about this because this side is always well defined and invariant on the choice of pH. And then one might expect this may be equal to homology of L. The reason for this is in periodic case, this floor homology of this M and this H, this Hamiltonian function H, is always isomorphic to this ordinary homology of M. So, which is not 0. So this means this implies Arnold's conjecture. Which says that there is always a closed, the number of closed orbit is bigger than the number of Betti numbers, sum of Betti numbers. But in the Lagrangian case, this actually is no in general. But in good cases, it is true, and I'll show you what are these good cases. So maybe y homology of LL is not L in general. This is because, for example, if you have a more easily, if you have a C and some circle S1, then floor homology of circle. This is floor homology of circle with pH of circle. So you can move your circle by just translation. You can move by translation, obviously. They don't have any intersection, so this is just 0. So this cannot be isomorphic to homology of S1. Okay, so in general, one cannot expect that the flow homology of Lagrangian is same as singular homology, and when they do, they would imply a very strong this symplectic property, such that by any Hamiltonian isotopy, whatever Hamiltonian isotopy you use, I mean, it still has to intersect itself. So that would be a very strong property of a Lagrangian submanifold. Okay. So now let's go about the statement if flow homology is defined. And what's the problem? So the easy example is.
By the way, it's flow homology of just n, but h is defined.
Yes.
What?
So this was the version where we have this.
Oh, this
Closed orbit.
closed orbit.
It's already defined.
Yes. If for non-degenerate H, but for degenerate H, it's not. So, and anyway, so okay. So if you call this L0 and if you call this L1, then one can immediately notice that you have two intersections, P and Q, and one is boundary of P, and you see one homomorphic strip, and remember that we had a condition that the bottom has to go to L0 and top has to go to L1, right? So this would not be a correct homomorphic strip because the top went to L0 and the bottom went to L1. So this is not. Instead, the other direction. This is a proper homomorphic strip because the bottom of this homomorphic strip went to L0 and the top went to L1. So there are two obvious homomorphic strips, and such that the top one contributes from boundary of P to Q, so it's 1 times Q, and boundary of Q is 1 times P. And one can show that everything else actually doesn't contribute. And so you see that boundary squared of P is boundary of Q is P. So boundary squared is not 0.
How can it be? How index? How can it be? The use of index is the indication of this method. P goes to Q and Q goes to P.
Maybe I can tell you later. You have to. It's not just for point, but you have to also take account these strips. So when you come back, it actually is it? Anyway, so I cannot do it on top of my head. So I mean, you have to do somehow something like you start from here and you go here. And somehow there is a standard way to move from here to somehow you fix some rotations to go from here to here. So maybe you suppose you went here and then you went back. So the total path would look like you go this way, and then from here to here you go here, and this is constant, and from here to here you go back. So this is something like you rotate it half of your circle, and so this is actually index 1, because this Lagrangian manifold is same as this Lagrangian manifold, and this half rotation is index 1, the full rotation is index 2. So this is actually index 1. Anyway, so the bottom one can be done. Anyway, so the problem is actually the problem is something like this. So for this, I have to first explain what is problem of compactness. So what this says is that it's a statement about the convergence of these maps. So if you have any sequence of J-homomorphic curves with
What does this example say?
bounded.
There are cases where this bounded map is not,
Yes.
where the
Yes.
homology is not defined.
Well, it's not. Yes.
But this when manifold is, or Lagrangian is not compact.
But it's a general situation. But in the Toric case, this is also true. But yeah, I'll explain. With bounded energy, converges, always converges to, if converges to a stable or broken homomorphic curve. So there are several terms I have to explain, just to give you a sense. Very much time. But, so what is energy? So energy is just symplectic. If you have a map, so any homomorphic curve, so you have a domain and a map to M, then you pull back symplectic form and integrate over your surface. So this is the energy. And because it's homomorphic, it's known that it's actually same as the L2 norm of your map. Because of the relation of symplectic form and the metric, if you impose the relation between the complex structure and so on. So, so somehow you have some, if it's bounded energy, you have some bound on the integral of your differentials, but the problem is that the integral is bounded, but individual differential might blow up at certain points. So that's what happens. So if you have a sequence of maps, so this is UN plus 1, UN plus 2. And what happens is at certain points, okay, so maybe I'll just do it this way. If you have sequence of maps at these points, somehow the derivative gets bigger. So at this point, derivative gets bigger, and at the end, the limit, at the end, the image would look like this. This is what's called stable curve, and you can actually, so you cannot define a map from here to here, so somehow to define a proper map, you have to actually add a component in your domain and then define a map this way. So this is the limit, the sense of the limit we are taking, and yeah, so there is a lot of analysis involved. And so the stable curve means if you have this kind of homomorphic strip, then it can degenerate into two strips, or this homomorphic strip degenerate into a strip with some disk attached, or strip with some sphere attached. Depending on where your energy blow up. If your energy blow up in the interior, then you get this picture. If your energy blow up here, then you get this picture. If your energy moves to infinity, then you get this picture. So depending on the limit you're taking, there are several possibilities, and this is Gromov compactness theorem. Okay. So the standard argument that boundary square being 0 is the following. So in Morse homology, so you look at some kind of height function h, and you look at critical points, and you look at gradient flows, you look at isolated gradient flows, and then you do the similar thing. So the generators are critical points, and the differentials are counting isolated gradient flows. Then one can prove that boundary scale is 0, because if you look at boundary scale of this point P, then what you're looking at is some kind of flow like this, together with some kind of so this flow this with the same endpoint. So you have, well, actually this point and this point is the same, but let's just write it in a different place. You have two flows, and always you have a connecting flow from one to the other. So for example, in this case, it's this, which goes from here to here. So what one expects is that to prove something like this, you have this homomorphic strip. So you take differential twice, and you want to say that there is a differential, and there is a differential, and it's connected by some big one-dimensional moduli space, which converges to, which limits to by compactness, compactness to this kind of thing. So this would be index 2 and index 1, 1, 1, 1, so something like this. But the problem is, again, this one. So this happens because this limits to this. One side, this limits to this, but on the other side, there is this bubbling. So you want to say boundary squared is 0 because you always have a pair of contributions from one to the other, so that they cancel each other out. But somehow you don't have a pair, but you have a pair with boundary squared with some homomorphic disk coupling. So in this case, this is not zero, and this is what happened in the previous example. So the best thing you can hope for is actually there is another pair. I mean, one of the easiest thing you can hope for is that there is another pair, so that this occurs in pairs, so that this one cancels with that one, and this is what happens for lagrangian. I mean, this Toric case. Okay, so that was one page of so that might be okay, right. So in the case of tangent bundle, so this is the case study by floor. So you have this zero section L, and suppose this is our tangent bundle, and then so let's look at very nearby Lagrangian submanifold, and it's known that and consider the case this is given by graph of, so this is one forms, so graph of df will give you a certain section here, and it's known.
This has a triple neighborhood of the
Yes.
Lagrangian
Yes, yes. So this is somehow local version in every situation, and this is always a Lagrangian submanifold. And in this case, if f is sufficiently small, C1 small, then you can actually look at what is the intersection of this graph. Let's call this L1. The intersection is where the differential form vanishes, and this is when df is 0, so it's a critical point of f. F is some function on L. It's the graph, and it's always Lagrangian manifold, and intersection is always the critical point of f, because df. Yeah, just any C1, any C1. And then so what Flo found is that if you have this kind of Morse flow on the bottom, so if you have a Morse flow, then one can always somehow lift this to a homomorphic strip. So in this sense, this Morse flow and homomorphic strip has one-to-one relation. So this is given by just using, there should be some Hamiltonian, so phi h or L. So you consider this as Hamiltonian flow of the original zero section. Then you just lift using this flow, then you can somehow define an appropriate complex, almost complex structure so that this becomes homomorphic strip. So Morse flow and homomorphic strip is one-to-one relation. That means the Morse homology of L has one-to-one relation with flow homology of this pair. So flow homology.
F and H have some relation.
Sorry?
F and H have some relation.
Yes, yes, yes. So H has to be defined on over L, and so it's some kind of projection to L and then taking function F.
F has relation with H.
Yes, I mean H can be constructed from F. So in this case, phi, graph L1 is isomorphic to just Morse homology of f, which provides, because f is a function on L, so this is homology of L. So in general, what happens is that this is so in a very thin neighborhood of Lagrangian manifold, this is what happens. And so in general, what happens is, for example, if you have a sphere and another Lagrangian manifolds, then holomorphic strips somehow are two types. So there is this very thin one, and which goes from this direction, and there is very thick one, which actually flows this way. So differential actually is differential thin plus differential thick. And this guy is 0, and the homology of this thin one is equal to just homology of L. So somehow this thick one changes the ordinary homology to something which contains this information about this Hamiltonian geometry of the Lagrangian manifold. So somehow so now considering the limit case when phi goes to f goes to 0, so this gets closer and closer, and so actually one can define different complex which looks like gradient flow with holomorphic disk connected by gradient flow and holomorphic disk connected by gradient flow and holomorphic disk, and so on. So this is anyway. So from this picture, the thin ones go to gradient flows, the thick ones goes to holomorphic disks, and so on. So this is some heuristic idea, and what O and Ono did is to define LL directly using singular chains. So all this argument involves gradient flows.
Excuse me. One more. What is thin and thick?
Thin is thin. Thick is thick.
Which is thin?
This is thin. This is thick.
Thin one looks like.
Thin one looks like this. So it's inside of. So it's written as a graph of one form f, where f is c1 close to 0. F is 0 and derivative is also 0, and close to 0. Okay, so what they define is this one. So let's say this. Actually, they work on cohomology setting. So let's just somehow function view of singular chains in L. I mean, there is some complicated story involved, so let me just skip. So just let's think of singular chains. So you take a chain P in L and define the differential M1 as M1 of P as follows. So you define this ordinary differential of P as P. So you look at this holomorphic curves. These holomorphic curves. So this would be this stick contribution, and now you have to record the image of holomorphic curves intersecting P. So that would be this one. And the way you do it is just you put a point here, and then you evaluate to the Lagrangian submanifold L. So you look at all images of holomorphic disks which intersect P, and look at the boundary. So this is the differential. So this somehow is a singular chain version of this picture.
So the first one is the sum of thing and the thing. dp.
So this is thin.
Okay, so that's just the same. Not,
This is thin.
Not both.
So
This would be the d thing in this one. Or?
this is thin. This is
Yeah, I mean, it coincides with this d thing you write over there.
yes, yes. And one might argue, well, there is one disk and there are several disks. And so the argument is, well, why? First of all, why is there several disks? So in general, if you have a big strip, and then you degenerate this, and actually this analysis I heard is very difficult, and so one cannot actually expect to prove that this really converges in mathematically correct sense to this one, but somehow one can heuristically see that it converges some flow here, and then here's some chunk which converges to holomorphic disk, and then flow, disk, flow, and so on. So somehow this has many, I mean, to set up this correctly is not so easy. So they actually just work on singular chains, which is still also not so easy. But so this is the differential. And okay, of course, now one wants to prove that m1 squared is 0. But we already seen that this is not so easy. So let's see what happens. So consider you consider this moduli space, and you take the boundary of this. So you are considering the boundary configuration of this, and one thing is, so these are the image of holomorphic disk meeting P, right? And the case that this holomorphic disk meeting the boundary of P is one of the boundary configurations. So it can be boundary P intersecting. So I mean, just think of family of holomorphic disks, and you have this P here. Then at the end, at the boundary of P, you have a holomorphic disk intersecting boundary P, which is the boundary configuration of this. So that's here. Plus, now by graph compactness, this disk might split into two. So boundary P. So that would be a good behavior, like strips splitting into two parts. But unfortunately, there is another term which bubbles here, or which bubbles here. So it's called disk bubbling. So in general, so because of these terms, it's a bit problematic. So let me, maybe I should take a break, but let me just do 1 more minute and take a break. So to record this phenomenon correctly, actually one immediately notice that now you have 3 points involved, not 2 points. So you have to actually define an operation with just not 2 mark points, but several mark points. So we define what's called mk of p1 to pk to be so the image of holomorphic disks, and look at only this part of the image. So this is your definition of NK. Then you can write this as, now you can think of this as another input. So this guy, without any mark point, this would be, in this definition there is no input, so k would be 0. So this would be m0. Okay, so this image of holomorphic disk. So this image, if you record the image of holomorphic disk, then that would be m0. So you can think of this as m0. So you can think of this as a product of m0 with boundary of p. Oops, oh no, not boundary, sorry. So this is p. That would be codimension 2. So you just take bubbling. So that would be m2 of p and m0 and p. So cyclic order is important, m0 and p. So this is m2 of p and m0. So p and m0. So the formula we have, so this is part of m1. So if you write it this somehow, if you correct all this, so one of so maybe we'll take a break.
The first two.
No, this is M1 of kind of M10, M thin of M1 thin of P. So this is M1 thick of P. But again, take differential with M1 thin of the whole thing. And this guy is, oh, I'm sorry, this is again P, not boundary P. So this is M1 thick of P, and again take M1 thick of P. So you see you have thin, thick, and, oh, sorry. So this is M1 thin of P, which is a boundary, and then you take thick, M1 thick. So you have thin, thick, and thick, thin, and thick, thick. But thin, thin is already squares to 0. So boundary squared. So you actually you can just include because it's already. So you have all the terms. So these 3 contributes this M1 squared, and the other 2 contributes the other one.
The second lecture will start
which is xi, ei. Now, this xi can be the sum of some formal, can be some formal sum involving this formal parameter t. So previously you didn't have this, but now you can actually solve this equation up to this formal solution. Formal solution is good enough. So because you can plug in formal variables here. So by looking at this some deformed infinite algebra, you can find more Lagrangian fibers with the non-Benish flow homology. So by generalizing your definition of flow homology, you find more and more. Okay, so maybe I'll stop here.